All right, thank you, James. So very briefly on my introduction, as mentioned, I'm Mika Kuronen and work as a planning manager here at Fluidit. I've worked pretty much my whole working career with modeling software, with all these different networks. Especially, I've been always interested in energy efficiency. So spending as little energy as possible for all the water distribution and sewage systems that we need to operate. We have a broad topic, energy efficiency, and short time. So without further ado, let's get straight to business. I have here some slides with some key points that I wanna point out. But we also have here our desktop software, so Fluidit Water, an EPANET-based modeling tool, from which I will be showing you some of the things that we discuss here. It's a short fictional demo model that I will be demonstrating these things with. So even though I'm talking about modeling, and I think it's the best tool to do all this, in some cases the only tool to do for this, of course the principles are general and can be applied with other tools also. So for content, I've divided this into 3 steps. So what I would say physical optimization. This means the actual pipe sizes, pressure zones, this kind of the physical infrastructure. Then we have optimizing controls. We want to talk about how do we control the pumps, from where do we pump, with what kind of settings and controls. And finally, the pumping efficiency. So how efficiently are we doing that pumping itself? I could say that these can be divided in roughly in 2 contexts. So the first 2 points, we are trying to minimize the required hydraulic energy. So we're trying to create systems that need as little hydraulic energy as possible. Then with the second 2 steps, thus meaning the controls are involved in both, we are more trying to produce that energy that we anyway are going to need. We're going to look at how we can produce that as efficiently as possible. Obviously, these are just general steps and some key points I want to pick up from each. And I want to also share some of the modeling results or these indicators through which I look at these energy efficiency issues. So first about physical optimization. So first of all, network sizing. I'm going to talk about and look at here only from the energy perspective. This is, of course, a broad topic and involves a lot of other things. But from the energy perspective, it's mostly energy due to pressure losses. So how much do we lose energy to the friction losses in the network? From my experience after modeling dozens and dozens of networks, its effect varies significantly. It's very important in some networks, and it's quite insignificant in many networks. Especially important it is obviously in long pipelines, as we have long distances, and thus they provide a lot of pressure loss. How would I look and approach it would be total energy lost to pressure losses. So instead of just looking at local pressure losses and looking at it as a pressure, we can also look at it as energy. It is hydraulic energy lost. It's a pressure with some flow. It is losing energy. So I would start estimating it by looking at the total energy lost to pressure losses and then comparing it to the share of the total energy. We quickly show you from our software side. So in Fluidit Water, there's directly a result that's telling you the energy lost due to these friction losses. Obviously, you could do that also as an additional calculation from other results. So in this example case, I have taken all the pipes from the network and summed up how much energy we lose to friction losses in this example model. For the second figure, I have taken how much hydraulic energy we are pumping into the system, so we can get a proportion of it. How big is it compared to that? Well, in this specific case, in this example model, we are talking only about 2 to 3% of the hydraulic energy pumped into the system is lost to friction loss. So in this example case, it would not be that significant. Wouldn't need to pay too much attention. But when I emphasize, this varies significantly network by network. So that's something I think always should be checked. Are we losing energy efficiency? Are we losing energy to friction losses? Second, I want to pick up pressure zones. So thus meaning the optimal division of network into pressure zones. And from the energy perspective, obviously we have the minimum pressures. So we'll be looking at ground elevations and pressures in the traditional sense, but from the energy perspective. One thing to remember, pressure reducing valves always lose energy. So yes, we can create lower pressure zones by using pressure reducing valves, but in energy sense, they are always losing energy. We have already done all that work to the water, and then we're just lowering the pressure down. Nonetheless, it has other benefits. So of course, it is sometimes a correct decision choice, planning choice to make. But from the energy perspective, it's good to remember that that's always lost energy. Key indicator, I wanted to pick up a result a bit different from just looking at pressures and things like that in your pressure zones, is how much energy is actually being used in some part of your network. How much hydraulic energy is leaving your network, and especially how much of that is extra. How much of that is above what would be required. Oh, again, let me show you a bit more here on the software side. I drew this in a time series because I think it's maybe easier to comprehend. So now, as just an example, I've taken a small part of the network and I'm checking at the results, how much energy is leaving the network. So this is with the consumed water and with the leakages, there's an amount of energy, flow and pressure leaving the network. So in this case, the green topmost would be how much energy is leaving the network, the total amount. Then we can start dividing that into pieces. Next, I have here required power at the blue line. So what this means, I've set up a limit of 25 meters in this case, so 2.5 bars. I've considered that that's the pressure that the users require, they need. And all above that is excess energy. That's energy that wouldn't need to be there. They don't need that extra bar or two of pressure. So this is how much energy we would need if even all the consumers would have a perfect 2.5 bars of pressure. And now their difference is then excess energy. What this tells us, I think this is a result or a way of looking at the energy saving potential. Obviously, this doesn't directly tell that we can just lower the pressure. That might lead to trouble in one place. But this tells us that we can easily look at different parts of the network or the whole network, and we can see the energy saving potential. Is it there or not? And if it is, then we start digging deeper into it. If it's not, we can directly see that, hey, this area of network, there's not much potential. Let's not waste our time and energy on that. So why I think it's better to look at energy rather than just pressures. Two major things. First of all, energies, we can directly link it to water. costs, price, or we can link it to, say, greenhouse gas emissions. We can directly make it something comparable, whereas 2 bars of extra pressure is just extra pressure. And the second major thing why I think looking at energy is the best way is that it takes into account both the pressure and the flows. Because it doesn't matter that we have high pressures if there's very little consumption in that area. We're not then wasting much energy. So it also incorporates both the extra pressure and the amount of water leaving the network. So that's kind of a view to pressure zones and looking at energy instead of just pressure. All right, final point here is reducing leakage. We'll not go more into that, just to keep in mind that obviously all the energy has also been done to all the water that's leaking out of the network. So reducing that will also be improving our energy efficiency. Next, optimizing controls. Once again, obviously a large topic and just a few key points that I'll pick up from here. Optimal pressures. We could think that what we try to do with controls in the end is that we want to have optimal pressures. We want to have as low pressures as possible with still satisfactory minimum pressures. That will lead us to least energy consumption and still have sufficient service level. Point out, usually optimal pressure is not constant, so use timetables. I mean, settings are varying according to the day of time. And one of my personal favorites, flow compensated pressure. I think that's one of the control methods that should be implemented more often. So it means we are driving a pressure setting, but that setting will increase if we have higher and higher flows. So that will enable us to keep more steady pressure at the end of the network or at the highest point of the network, thus enabling us to lower the general level of the pressure most of the time and thus saving us energy. Production optimization, so I mean where to produce the water, and also in the network, if you have multiple routes, how should you guide that water around the network? Also here, not only how much energy goes into the treatment process, but also how much goes to the pumping, and onward, how much goes to the pressure boosting stations in the network. Thus, you can't simply be looking at a single water treatment plant and start optimizing that. You might simply end up spending more energy somewhere else in the network, say at a pumping station, and end up with more energy consumed than previously. That's why I think it's important here to look always at the big picture. In the end, the key indicator is the total energy used by all pumps. What's important here is that you have the full control system modeled. So if you have for all your plants and booster stations, you have the exact controls that they in reality have. So your system responds to your different settings and things you try out in as realistic way as possible. So you could look at graphs like this. You can obviously have those different plants, their consumption, their energy consumption, maybe calculate specific energies, how much it is per cubic meter, etc. But then always keep your eyes in the end on the total energy consumption. These will just give you a hint to what maybe we should produce a bit more here as it uses less energy. But it might not be. You need to try out and follow the full energy consumption by all pumps. And this is important that you have the full control system modeled here. In Fluidit water, that can be done in several steps. So the basic easy controls, most common controls are directly in the graphical user interface. So constant pressure, constant flow, they can vary according to time. But you can also use EPANET-based rules and controls if you have more complex controls. Those already enable you to do quite a lot. And then as a final step, if you're not enough and you have even more complex systems, all of those are also possible to model. In Fluidit water, you can use Python scripts to model as complex control algorithms and systems as needed. All right, that was just a few key points to pick up from control side. Talk a few words about pumping efficiency. So in the end, this is about pump sizing and optimization. It can be either for existing pumps or it can be for new pumps. It's good to remember that generally speaking, pumps are quite cheap compared to the energy they consume. So don't hesitate to suggest new pumps. They can quite easily save their cost quite fast. The number of pumps are all same or different. So also not just looking at the whole pumping station, but if you have parallel pumps, they might be even of different size. How should you run them in parallel? Include electric motor and variable speed drive. If we want to model the pump's full energy consumption, see how we can best improve it, we need to include the electric motor and variable speed drive. It's not enough that we look at the pump's hydraulics. We also need the things running the pump. Key indicators here, well, total efficiency, so-called wire to water. So from electricity to hydraulic energy is obviously the most common one to look at. And its components, so as mentioned, also go down to electric motor losses and variable speed drive losses. They are what composes the whole efficiency. And then at the same time, it's worth remembering, in the end, we are minimizing specific energy per cubic meter of water. So even though efficiency is a very useful parameter to follow, in the end, it's not what we want to maximize. We want to minimize specific energy. So what I mean is that efficiency simply tells how big proportion of the electric power we get into hydraulic power. It doesn't take into account if we waste that hydraulic power, for example, to the pressure losses that was discussed earlier. So we might pump really fast, we might have a good efficiency, but you might waste all that energy to pressure losses. So in the end, we want to minimize specific energy. So in this case, let's have a look at a few graphs. What you could start with is looking at all of your pumps. So in this graph, I have all of my pumps together and looking at the proportions. In this case, 19% of the electric energy goes into electric motors losses and variable speed drive losses. 24% goes in losses in the pumps, the hydraulic losses. And finally, 57% goes into the actual hydraulic energy, pressure and flow energy of the water. So once again, you could start by looking at the big picture. What's the total amount of energy and how is it divided? Then, of course, going down to dig more and more details. Let's update that one. Going to more and more details on a single pumping station. So here you would have a flow head representation of one pump running and two pumps running and their efficiency. And go all the way to digging these different components, how they vary in time, etc. All right. Few final thoughts. Last slide. We are running short on time, but luckily also running short on slides. Look at the system as a whole. That's maybe one of the key points I want to here make. Minimizing energy in one place might just move that somewhere else or even increase the total energy. Get the general view and the big picture. First, look at things, the whole things. How much energy are you consuming? How much of it is going to which losses? How much of it's hydraulic energy? And then start digging deeper and deeper. Is it wasted on pressure losses? So where is the energy going? And full-scale detailed modeling is the tool to look at the whole system. And by full-scale detailed model, I mean that you have all the pipes, you have all the consumers with their elevations, you have the real controls, control system fully modeled. You have the pumps, and not only the hydraulics, but also the electric motors and variable speed drives. Only this way you can actually get the whole big picture into your hand. And just finally, obviously I've pointed this out here in some steps, but in reality it's an iterative process. So it would be an ongoing process, and you change something and go back to optimizing earlier steps and so on.
Awesome, Mika.
Thank you on my behalf.
That was just great. Thank you very much for the presentation. And we actually had some questions in the chat, and I had some questions from before that were submitted. So James Clahar asks how we would go about optimizing source abstraction with varying license constraints. So average, maximum, daily, monthly, yearly volumes. And I think this is an area you've had some experience with.
Yes, a good. I would start approaching it maybe in two different levels. So I would look at how complex is the system, how many of these plants do we have, and a bit depending on that. So if it's a relatively simple system, we could simply manually make different scenarios and try out at different consumption days, how much do we take from each plant. But if the system would be more complex and harder to optimize, those Python scripts that I briefly showed, we can implement those to any of that. So we could actually start making full optimization algorithm for that. That would say follow how big percentage of the monthly yield we have already used, and then according to that increase or decrease water from one plant, etc. So a bit depending on the complexity, but all of these are possible.
I think I just had to let him back into the meeting maybe halfway through, so he caught some of it.
All right. Well, maybe you can hopefully check the recording too.
Yeah, we can put it in the recording. You also there was a point where you mentioned about leakage detection, or at least that leakages can be a source of losing energy, and so I thought it could be interesting to talk a bit about how far leakage detection can be driven and understood in Fluidit's water software.
Yes, so leakages are of course a broad topic, and I think one of the key points is what kind of leakages are we talking about? Are we talking about small constant leakages from various parts of the network, or are we talking about a larger leakage? So single large leakage is usually easier to detect, and those can also be modeled. So we can start running mass analysis, running hundreds of simulations, try with different leak places, and see which results would best match with the measured pressure measurements. So the kind of big leakages would be approached mostly this way.